All right, so good morning from me. My name is Oliver from Hioki Europe in the marketing department, and today we are presenting a webinar titled "Aiming for 100% Efficiency: The Future, Power Measurement Challenges and Solutions." And before we start with the actual topic, I just wanted to give a little introduction to today's webinar. All right, very quickly about Hioki. As you can see, Hioki is a Japanese company founded in 1935, so about 86 years on the market, and Hioki is producing electrical measurement instruments. Nowadays, we are producing a wide range, not only what you see here, about 200 main products we have on the market, starting for instruments for electro installation and maintenance, like digital multimeters, insulation testers, clamp-on testers, but also more advanced instruments for R&D or manufacturing, such as memory recorders or battery testers. We have power loggers, data loggers, and also power measurement instruments. For Hioki, precision and quality is well known and is appreciated by customers worldwide, and it's really one of our focus to get to bring out new products with new innovative technology. One of the outstanding areas for Hioki's innovations are electrical sensors, such as the current sensors we also talk about quite a bit today. And this sensor technology is well known for the accuracy as such, but also the fact that Hioki is the only test and measurement manufacturer who actually designs and produces those sensors, and also the measurement instruments is quite a special or a unique positioning of Hioki. Today's webinar will cover some of the advantages there, and I shall hand over to the person leading through today's topic of aiming for 100% efficiency, my colleague Roy Harley, who will take over from here.
Okay, thank you very much, Oliver, for the introduction. As mentioned, my name is Roy Harley. I'm a product marketing specialist at Hioki Europe. And in this webinar, we will address the challenges of accuracy power measurement of today's power electronic devices and systems, and we'll introduce solutions to meet those challenges. What kind of challenges are we going to look at? We're going to look at the use of GaN and SiC semiconductors, and a trend that we see where the voltage of the systems is increasing. After we have looked at the challenges, we will take a brief overview of the PW8001 and the new lineup of current sensors that come along with it. And after that, we will focus on the applications that are suitable for this measurement application. So let's start. Designers are using more SiC and GaN semiconductors nowadays, but why? What makes them so interesting? And what is required to accurately measure the loss and efficiency of SiC and GaN-based applications? To explain this, I would like to take an ongoing development of EV as an example. It is clear that car makers are in a constant process to increase the range of their cars, to reduce the charging time, and to cut manufacturing costs. As a part of this, they improve software. So you regularly get software upgrades. Think, for instance, about a better temperature management of your batteries, or to optimize the software of the electrical drivetrain. However, there are also constant developments of the hardware of EVs. Downsizing of the powertrain is a very good example. In the middle, you see here a drivetrain for an electrical vehicle. And what we see nowadays is that car manufacturers and tier one suppliers are aiming to reduce the size and integrate different parts of this drivetrain in one assembly. For instance, the inverter and the reducer are combined with the electrical motor to efficiently use the space inside this configuration. One of the most important and big parts in an inverter of this type is the step-up inverter. Here you see it in the electrical diagram, and here you see a picture of a step-up inductor. Because it has to handle the power of the powertrain, the size of this reactor is quite big, and the power that it needs to be able to handle is equivalent to omega L, where omega is the rotation frequency and L is the inductance. So if the aim is to downsize the reactor, the thing that we have to do is to increase the rotation frequency, and that can be done by increasing the switching frequency of these semiconductors. Well, SiC and GaN are semiconductors that are able to switch at higher frequencies, and they also have a lower switching loss than traditional silicon-based semiconductors. And that's why they are becoming more popular. But there is a downside to this way of developing, and that is that it's much more difficult to measure a high frequency power more accurately. As soon as you're talking about 50 kilohertz or more, it becomes more difficult. And I will explain you why in the next slides. The first challenge that we are meeting when we are going into higher frequencies and measuring, for instance, low power factor products is the fact that we have to measure power. And power, if you need to want to measure power accurately, you have to measure the voltage accurately, the current accurately, and the power factor accurately. Well, the voltage normally is not a very big problem, but the current and the cosinus phi and the power factor are more difficult. So if we start with the cosinus phi, it is shown here when you do a low power factor measurement, for instance, with a burden resistor or a load resistor, which has a high power factor, you see that the active power is very high in comparison with the power error. However, if you're going to do some measurements on a low power factor applications, for instance, like a reactor that we spoke of earlier, then you see that the active power is quite low in comparison to the power error. These two examples show that it is essential to eliminate the phase error that we have in the power measurement. First of all, I will explain that the power measurement is done by measuring the power accurate, the voltage accurately, the current accurately, and the power factor accurately. In general, the voltage is quite simple because normally that is measured with a direct input. But for the current, there is a different situation. All the different kind of methods to measure the current for power have their advantages and disadvantages. For instance, internal shunt resistance have a low resistance and are by nature inductive, which makes them unattractive for high frequency measurements. And as we have discussed earlier, in power electronics, we see a trend that the frequencies are going up. Hioki is predominantly using external current sensors that have a voltage output, and at a nominal input current, they will provide 2 volts. This type of current sensor will cause a phase error, as can be seen in this frequency diagram. The red curve shows that that it's already noticeable above 10 kilohertz that there is phase error. You might think that this kind of current sensor is not suitable for power measurement applications, especially not high frequency ones. But that's not the case. And the reason for that is that Hioki is manufacturing and designing current sensors that are meant for power and measurement that are very constant in frequency characteristics. In other words, all current sensors with the same model code will have identical frequency characteristics. With this in mind, we can work out a method to eliminate the phase errors. All new Hioki current sensors have an internal memory, and in that memory we store some data. That is, of course, the sensor model, but also the phase shift error of that particular current sensor, the rated current, and the serial number of this current measurement. When a current sensor is connected to the new PW8001 power analyzer, it will be recognized automatically, and all relevant information like phase error information, serial number, and a rated current will be registered in the PW8001. On this slide, you see two screenshots of the PW8001. And here on the left-hand side, you can see that in this situation, we have connected a new series current sensor to the PW8001, and all relevant data stored in the memory of the current sensor are now available for the power analyzer. On top of that, also the power analyzer has recognized the phase shift error of this current sensor and has automatically set the values for a phase shift correction. And with that, we eliminate the phase error over the full frequency bandwidth of the power measurement. In other words, you don't have to worry about phase shift errors anymore. We call this automatic phase shift correction, APS-C, and it's a plug-and-play solution and unique for power measurement nowadays. The second challenge that we are facing is the interference of high switching frequency noise. For that, we are going to look at the reactor loss measurement as well. Here you see a typical diagram of reactor loss measurement. So you measure the current through the reactor and the voltage drop over the reactor. And you do this at a frequency of 100 kilohertz, as you can see here in this screen shot from the power analyzer. The voltage is switched at a frequency of 100 kilohertz. And this is generating noise. And if you use a current sensor that is not protected against noise, you get a measurement as shown in I2, the blue curve. You see that there is high frequency noise at every switching moment of the semiconductor here. But it can also be different, as you can see here in this yellow trace I2. And this is a CT69-4 current sensor, which has a very high common mode rejection ratio, as you can see here on the right-hand side of the slide. It has 120 dB at 1 megahertz common mode rejection ratio. The 120 dB is the same as 1 ppm or less of influence of external noise. And yeah, you can understand that we can then neglect it in the measurement result of the current measurement. We achieve this by sealing the sensor head of the current sensor with a aluminium box, which is completely sealed, and by using very high quality cables to connect the sensor to the power analyzer. The third challenge that we meet is the challenge of signal strength. Our competitors have to rely on third-party suppliers of external current sensors. They normally use current sensors that have current output, and they connect them to the internal measurement shunt of the power analyzer. This is different for Hioki. We develop and produce the power analyzers and the current sensors ourselves. Let's look at an example. Imagine that you want to measure a current of 100 amp. In the situation of the Hioki current sensor, and we are looking now in this case at the CT6873, the output voltage that is generated at a current value of 100 amp is 1000 millivolt or 1 volt. If we, however, then look at the situation of one of our well-known competitors, and we want to measure the same 100 amp, that current sensor has a ratio of 500 to 1, meaning that at a current input current of 100 amp, this current sensor is generating 200 milliamp output current. And this output current is then connected to a low ohmic input shunt, measurement shunt of the power analyzer. And as a result, the input voltage that is offered to the input of the measurement circuit is only 16 millivolt. In other words, if we compare the two situations, you can see that the Hioki solution has 62.5 times higher input voltage at the input of your measurement circuit. Now you can imagine what kind of effect that will have on your signal to noise ratio. The fourth and the last challenge that I would like to introduce is the increase in system voltage. We see nowadays that, especially with industrial solar farms, 1500 volts DC is becoming the standard. You will think, well, that's not really a big issue because I have a power analyzer and it has a range of 1500 volt, but that's not really the whole story. I will look into that a little bit later. But you need to have a power analyzer that is able to evaluate the development and test the inverter or the power conditioner that you are developing. Another application which can be used in this situation is also storage, energy storage. And if you want to have the energy storage connected directly to your solar panels, also this system needs to be able to be measured at 1500 volt. A second area where we see an increase in voltage, system voltage, is for electrical trucks. There are at this moment already truck manufacturers that are looking at system voltages of 1200 volt. For regular cars, we have 400 volt DC system voltage or 800 volt system voltage, but for trucks they are now looking for 1200 volts, and therefore it's also important to be able to measure the battery voltage at the same rating. So then I need to tell you a little bit about the safety standards, the international safety requirements for electrical equipment for measurement, control, and laboratory use, described in the IEC 61010-1 edition 3.1, will become effective starting on the 1st of January 2022. So if you have a power analyzer and you want to do measurements above 1000 volt, as of the 1st of January 2022, it's not sufficient to use a power analyzer that has a range of 1500 volt and is cut to qualified according to the IEC 6110-10 edition 1 of a previous edition. The PW8001 is the only benchtop power analyzer at this moment that is complying to the IEC 6101-1 edition 3.1. And you need this because you need a Cat2 instrument to be able to be used in a laboratory of a manufacturer that has a Cat2, how do you call it, statement, or is a Cat2 environment. And therefore, it's it's something to think about when you are using high voltage testing. As we have now discussed the challenges for power analysis, I would like to go to the introduction and look a little bit more about the PW8000 and the current sensors. The PW8001 has a 10.1-inch touchscreen, and it can have up to 8 different power channels. The basic accuracy of the system is 0.03%, and for DC it's 0.05%. The maximum sample frequency is 15 megahertz, and the resolution of the AD converter is 18 bits. It can measure up to 1500 volt Cat2 according to the latest IEC standards. And there is the automatic phase shift correction function that we have already discussed, which eliminates the phase shift error. If we look a little bit more into detail about the measurement units, then there are 2 different measurement units. The U7001, which is used for high voltage measurements, and the U7005, which is more used for the high frequency, high accuracy applications. I will take a closer look into these in a later slide. It is possible to make your own selections of the input modules, and they can also be positioned in a random order inside the instrument. Looking more closely at the 7001, we see that the basic accuracy for 50 to 60 hertz is 0.07%, and that it has a sample frequency of 2.5 megahertz and a bandwidth of 1 megahertz. It's able to measure up to 1500 volt DC, and with this kind of features in mind, this input unit is very suitable for measuring DC power or grid-related power. So, for instance, with a solar converter. But it's also suitable to measure the loss of IGBT inverters, and that's in combination with each other makes it quite suitable for converters or inverters that are connected to the grid. And all of this is offered at a reasonable pricing as well, which is probably also interesting for you. If we then look at the U7005, which is the high accuracy input module, we see that the basic accuracy is 0.03%, and that the sampling frequency is maximum 15 megahertz, giving the power analyzer a bandwidth of 10 megahertz. It has 18 bits AD conversion, or sorry, I mentioned 10 megahertz, but the bandwidth is 5 megahertz. My apologies. And it can measure up to 1000 volt DC. Because of the high sampling frequency and the high accuracy, this instrument is ideal for the development of SIG and GAN applications. And also, in combination with the automatic phase shift correction function, it's a very useful instrument, an accurate instrument to evaluate the loss of inductive reactors, where you need to measure your power vector very accurately. The next thing that I would like to address are the two available options at this moment for the PW8001. First one being the 4-motor option analysis function, and the second one waveform and DA output function. The 4-motor analysis function, it makes it possible to measure up to 4 mechanical power at the X of motors, electrical motors, instantaneously. So here you see a picture of a high-performance e-vehicle with in-wheel motors. So you can measure all the mechanical power of the 4 wheels instantaneously. And that's very useful when you want to tune your system and make sure that the power is distributed evenly over the wheels, or in different situations that you want to have a different power management or a distribution. It's not only limited, of course, to EVs. Also, interesting applications are all kind of drones and industrial robots, where also more motor drives are combined in one solution. The second option that I would like to address is the waveform and DA output function. This function is useful if you are interested in capturing your waveforms of voltage and current for a longer period. This output has the possibility to output 8 waveforms of voltage and current at a sampling interval of 1 megahertz. So if you connect it to a memory recorder like the MR6000, you can capture the waveform of the voltage and the current over a very long period with a high resolution of 1 mega samples per second. Another way to use the output is to use analog outputs. The analog outputs are basically the calculated values of your power analyzers output in an analog way. And the update rate of those signals is 10 milliseconds per second, or a 10 millisecond update rate. Also, this provides you with a lot of information of your system, and it can be very useful to store for a longer period. Having spoken about the power analyzer, I also like to spend some time on the new current sensors, because as we have already seen earlier, the current sensor is an essential part of an accurate power measurement system. As mentioned already, the current sensors have an internal memory, and as soon as they are connected to the power analyzer, the information becomes available and settings are made accordingly. And here you see once again the information that is stored into the power analyzer. If we look at our pass-through current sensors lineup, you see here an overview of the frequencies that they can handle and the current that they can handle. Here you have some pictures of the applications which are applicable for the wavelength range and the current range. And here you see the different current sensors, the pass-through current sensors that Hioki can offer. I would like to mention 2 completely new current sensors, and that are the CT6873 and the 6872. Both have a very high accuracy of 0.04 of reading and 0.008 of the full scale. But even more impressive is the frequency bandwidth of these current sensors. The 72 has a bandwidth of 10 megahertz and the 73 has a bandwidth of 5 megahertz. When you look at these kind of specifications, then you are right if you think that these are the right current sensors to develop GaN and SiC applications that are using high switching frequencies. Then I have here a slide with the clamp-on current sensors. Maybe you think that clamp-on current sensors should not be combined with a high accuracy and high spec power analyzer like the PW8001. But we think that they have some interesting features and that these are worthwhile to mention. For instance, the accuracy of the current sensors is 0.3% of reading and 0.01 for the full scale. For clamp-on sensors, that's unique in the market. Also, the temperature range of this clamp-on sensors is very wide. You can measure from -40 degrees Celsius up to 85 degrees Celsius. These two specifications make them very popular for WLTP testing in the automotive industry. But also looking at the limitations in bandwidth, because you can see that the scale is a lot lower. They're a lot more into the left side of the application field. If there is no need to have a high bandwidth, then it can also be considered to use this kind of clamp-on current sensors, which are a lot easier in use than, of course, the pull-through of the pass-through current sensors. So for situations where you need to do a setup where it's not so easy to disconnect your cables, still this can be a valid solution as long as the bandwidth of your measurement is not that high and your requirements for accuracy are not that high as well. Okay, then we go further to the next chapter, which are the applications. We start with two different 8-channel applications. On the left-hand side, you see here a dual inverter motor drive for a performance EV. In this situation, you can use the U7001 to measure the DC input of your inverter. If you for the output of the inverter, which has a much more high frequency components, it is necessary to use the U7005 input modules. So in this situation, you use 8 sensors, and these ones are the high accuracy ones, which also have the automatic phase shift correction. And for this one, you can use the U7001 with the lower input. And this has an advantage because when the system voltage would exceed 1000 volt, you can still continue using them. Another application where it's useful to have 8 input channels is a power management system for solar power. These systems are becoming more and more advanced. It's not only collecting the solar power from the panels, but there will be also an increasing need for energy storage, because net access is not guaranteed in the future. Because of the capacity of the net to absorb all kind of renewable energy, it might be that it's not so easy to connect to the grid all time in the future, and therefore the storage option is interesting. Also, we probably will start driving EVs in the future, and therefore also it would be useful to have a DC-DC charging for your electrical vehicle in combination with storage and of course the solar power. So If you are developing a system like this, it is essential that you know what the dynamic behavior, the dynamic power behavior of your system is, so you can optimize it for all different kind of conditions. And therefore you need also a lot of input channels. And in this case, we are using and showing 8 input channels. Then we come back at the SIG and GAN applications. As already mentioned before, what in this kind of applications is important? Yeah, we try to increase the switching frequency of your switching devices to be able to reduce the size and weight of your step-up reactor. In this kind of application, of course, the automatic phase shift correction is of very high importance, but also the DC accuracy and the sampling of 50 megasamples per second. And then to have more inside information about the dynamic power behavior of your powertrain, it's also useful to know that we can offer an update rate of 10 milliseconds of the power measurement results without having to compromise on the accuracy of the measurement. The second one is electric drive in general. What are key things in this kind of application? Of course, again, the high-speed 10 millisecond update rate and the automatic phase shift correction function, but also the accuracy at the DC side and the ability to measure up to 1500 volt at the DC side. So you can make sure that for this kind of vehicles, you are future-proof. So if the system voltage would increase, you are able to measure that with this device. The third and last application that I would like to mention is wireless charging. You can see here 3 applications down here. For instance, the automated guided vehicle that is used in logistics centers. As soon as they don't have a job for it, it will go to a charging station to be charged. And also, of course, the wireless charging of EVs and the wireless charging of electrical vessels is important. As this circuit is switching at high frequencies, the standard is about 85 kilohertz. It is necessary to have a high sampling interval to do an accurate measurement. Also, the phase shift correction function, automatic phase shift correction function, will contribute to an accurate measurement of this application. As we're talking about bigger currents and high frequencies, also noise resistance is a very important factor. And of course, to be able to measure the efficiency of the system accurately, it's also necessary to have a high accuracy, not only at the low frequency side, but also here at the high frequency side. Okay, that concludes the presentation of the PW8001. I hope you understand that it is our mission to provide true power analysis for engineers in pursuit of power conversion efficiency. The PW8001 power analyzer and new current sensors will be released in the middle of December this year. And if you would like to get more information about the product, please visit our landing page with the link here at the bottom. Okay. And that finishes the presentation, and I would like to continue to the Q&A session. Oliver, have we already received some questions?
We have some, meaning one question at the moment. From Mr. Paulo Toro, we have one question, and very short, very quickly. Internal data storage depth. What is the internal data storage, or is there?
We are at this moment, I'm not certain what the internal storage is, but there is a possibility to store data, and that is done on a USB stick. And of course, the instrument also has a LAN interface, and through that LAN interface, also real-time data can be stored on external drive.
Okay.
Yeah.
That's answering the question.
Yeah, I think so.
Also from Mr. Paolo Torri, PC data transfer app. Is there one?
Yes, there are applications where you can store the measured data on a PC, and that can be done in a real-time sequence. And as we discussed also about one of the options, we can use a analog output to get out the most essential data and store it on a memory recorder. Yeah.
Okay. So these are the only questions at the moment. So anybody, I don't know if there's any questions left, and now maybe now's the time to ask them. If there's any questions after the webinar, of course, we also have contact details, and you can follow up on that. We are more than happy to come back to you and discuss in depth about your applications or whatever questions appear to you just after we finish the webinar.
Okay. And then.
Okay, there's more coming up.
Yeah, there's more coming up. We are part of the product support group, product marketing group. And I would like to also introduce briefly my three colleagues. So if you have any questions related to this product or to any other Hioki products, you can send this to the Hioki EU site or email address, and then if it's a technical question, it will come to us and we will take care of it.
Yes, while you were speaking, Roy, we have two more questions. Do you want?
Oh, okay. Yes, of course. We go back to the questions.
All right. So there's one from Mr. João Adigas. I hope that's correct. Power modules are field upgradable. That is the question.
No. They're not field upgradable, and the reason for that is that we're talking about a very high accuracy measurement instrument, and so if the configuration of the setup would be changed, then also this system needs to be calibrated, and that cannot be done in the field. Probably in the future at Hioki Europe, we will have a calibration system where we can install new power modules and take care of the calibration.
Yes, okay, thank you. That one, and then we have one more. Is there a potential separation of the individual channels, or do they have a common ground?
No, all the input channels are isolated, and therefore, you don't have to worry about any how do you call it, crosstalk or whatever. All of them are fully isolated with optical coupling.
Okay. Then there's one more. Synchronization of multiple units, question mark.
Yes. It is possible to synchronize two power analyzers, and that's done with a optical link. However, this option will become available in 2022. At the release date at the end of this year, that option is not available, but it will come soon after the release of the instrument.
Okay. Well, while we're talking, one last question, the last probably, and I hope I get it right because a lot of information in there. Okay. Is it possible to estimate the accuracy of the phase shift? For example, F is 150 kilohertz, max voltage 500 volts, max current 15 ampere, and a phase shift angle of 89.51 degrees.
I think that we are going to come back to you with an answer because that's very difficult to reply to at this instant. But I think that the accuracy of the phase shift function, we can send you some information about that after the webinar. Yeah.
Okay. Very good. All right. Yes, as we so Roy already mentioned, we have a contact email where all other questions can be addressed to us. We also will share the presentation materials as a PDF right after the we ended the webinar, and we will also share the recording so you can recap a bit of the explanations from Roy about these slides. Okay.
Yeah. And then there's one last thing that we would like to mention. And that is that we have a new public webinar on November 10th, and the content will be solutions for battery industry, test and measurement solutions for the battery industry. Okay.
All right. Well, then I would like to thank for everybody for joining today's webinar. Hope you found it interesting, and I want to thank, of course, Roy for the explanations and leading through that topic. We are looking forward to keeping in touch about power measurements and other topics as well, and hope to see you again soon in the next upcoming webinars.
Okay.
Right. So, thank you very much, everyone. And have a good day.
Bye-bye.
Goodbye.